Okay, I think yeah, we should start. I just continue. That's the major idea. Yeah, that's say. That's the major idea. That means, the all is really is eigenvector, where is the local rotation axis. Yeah, that's what I say. Well, I give a definition. What means local rotation axis? Because local, rotation axis, they can only, stretching or compress. They cannot rotate by itself. Well, that's I give these definitions. Some professors says this looks like an axon, axon. So it's not like axon. Well, I just give this kind of definition. Fortunately, there's nothing else. It's eigenvector. So we define the rotation. Rotation, cannot rotate it. Only can stretching or compression. It is really eigenvector. So well, the definition is, well, this is definition or axon. We say, well, we just definition. Okay. And then how to know the new text? As I said, vortex have no correlation with shear or stretching. You cannot say shear stretching. It is rotation. You cannot say. Rotation must be angular speed. So, as I said, fluid angular speed is linear correlated with nu-tex. Well, how do you know that? That's the proof. Well, we also call principal decomposition or principal coordinates. We have the principal coordinate matrix like that for lambda, 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 stretching and compression. Or rotation, epsilon c epsilon c eta shear. The three parts, three metrics, submetrics. So really, this is rotation. So this is rotation because R over 2. So really nu-tex is twice of the angular speed. This is angular speed, yeah, in the principal coordinates. So the nu-tex satisfies this condition. Suppose vortex is A, B, C, R is the rotation, S is the shear, C is the stretching. Well, apparently, B should C and should be 0. So only A is 1. Only A is 1. So vortex equal to R. AR. Well, really it is, I think, if we talk, angular speed is 1/2. Oh. So that's only the nu-tex is correlated to the rotation. Only. No others. That's what I said. No matter Q, lambda, CR, lambda 2, they all related to shear. All related to shear. That's what our definition. And I explain that, I just say, is some people have questions. One question is say, well, you give a definition of point. We talk about vortex. Vortex is a group. Many people ask the question. Vortex is a group. You talk about nu-tex a point. Why is a nu-tex vortex? Is vortex? They're different concept. Well, when we talk about mathematical definition, we only talk about 1 point. If your definition not stands at 1 point, how the definition for whole group? That means the definition must correct to 1 point as well. We only talk 1 point. The 1 point that we need to find the axis, we need to find the strength, angle speed. That's what I say. we only can give the definition for one point, all of them. All of them. Temperature, pressure, vorticity, luminosity, we define in one point. So new text is not extra. It is definition for one point. I don't think there is any mathematical definition for house, for cars, for ships, for trains. Do we have mathematical definition for house? I don't think we have. This group. Even for Toledo, how to give definition, mathematical definition. There's no way to give the definition. Definition only give one. Well, if one is not standing, how about the group? We must meet at one point. Also, we say the vortex definition must be Gaussian invariant and in the inertial coordinate system. That's what we call the Gaussian invariant. Also, I think the vortex accurate definition must be objective, is what I say. Which means they must be same, no change in any coordinate system. They should be. Any coordinate. Because they cannot change because use different system. So, well, this, I think, Dr. Yu will talk about this core line and objective. The core line and the objective, they are not related to the coordinates. Yeah. Well, then talk about nature. We talk about nature. We talk about hurricane. We talk about tornado. You talk about point. Well, we still can use this new text to find group, but we call this called the new text core line. Really, is the local largest new text, local maxima. But new text core line is local maxima is unique and threshold free. So they say, well, your new text is still need a threshold, well, need to improvement, not very much. They will say that, no. New text core line is threshold free. They give unique vortex structure. If we don't have threshold, it's unique, not related to the threshold. I think Dr. Yu also will talk tomorrow about new text core line. So we need to meet this kind of principle. Yeah. Well, that said, new text definition again, we just say, well, something like that, and yeah. Well, this is not good. We talked about that already. The velocity increment, I talked about this already. So we have to make difference by the dot product or dyadic operations. We need to be careful with that. Yeah, that's what we say. Yeah, we cannot randomly move or come back for the dot product. We cannot do that. We cannot remove the dyadic as well. We cannot do that. The most, I think, textbook they do that. Local rotation vector, as I said. Well, we talked this already. Yeah. Well, stretch only. That's what I said. It is. When we talk the matrix, this is gradient of V transpose. When we talk about mathematics, that's the eigenvector for this, not for this. This is velocity gradient, not for water gradient. It is a water gradient transpose. That's said. One of the reasons why we need 160 years to find a new text we don't need it. Yeah, because there's a mathematical misunderstanding. I see. That's why we need a long time. Okay, I come back to this. Yeah. Well, we come back to this. Well, as I said, well, we use this. This is correct. Then we need a transpose. If we don't use that, we directly use original this, the mass, the matrix. Then we find that I did calculate this T active. It's totally different from mutex. This is a vector. It is also eigenvector. It is an eigenvector. Yeah. But this eigenvector, it is not all, not the mutex. I didn't, spend a long time to study what this eigenvector is. It is an eigenvector, but it is not a mutex, not a rotation axis. No. No, not really. Well, this is just repeated that. Just repeat this. As I said, well, we cannot do that. Yeah, we cannot do this. Yeah. You see the difference again. Is dot, not dot. There's no T, there's a T. So that's one of the problem. Cost, we get a wrong answer. Well, then we talk a little about coordinates rotated, because we need to find what we call principal coordinates. What means principal coordinates? Very simple word. We just use this eigenvector as our coordinate, one of the axes of our coordinate system. But first, we need to understand how to do the rotation. Well, the 2D rotation, we can use this. Well, this is the gradient of velocity. This is the rotation. After that, you get a new origins of partial small u, partial x. Now you got partial capital U, partial x. This is we do the rotation matrix. Rotation by two rotation matrix. Yeah. Well, only difference is negative sine theta. So we use that, or we PTP. That's Z orthogonal. It's orthogonal matrix. We need to use orthogonal matrix. That means this matrix times this matrix is identity. Is identity. So we need to use this to finish the rotation. We need a rotation. Why we need a rotation? The reason is we want to rotate z, original small z. Well, where's z? This is x, y, z, the 2D. Well, 3D, where z. We want to rotate z to our eigenvector. That's our purpose. So we should use that. Well, so we try to find the rotex, rotation or coordinate system. That's what we want to do. Q, one vector. This is one vector. Q2 is another vector. Q3 is a vector. That's the three vectors. That's the root vector. They must be orthogonal each other. We must. That's what we call we call the rotation matrix. Here, the Q is here. Here we use Rx, Ry, Rz. What is Rx, Ry, Rz? That's the mutex three components. Small x, small y, small z is originally coordinates. The mutex has three, projections: Rx, Ry, Rz. Okay, and of course, the transpose is that one. Well, I think we need Q and Qt, they are orthogonal. Well, when we use this, so we say well, did I write something wrong here? Oh, okay, we use the QT as here times RX is 0, 0, 1. That means we finish rotation. If we use this, this is new text, right? In the original coordinates, and this is 3 components. Then we do that because they are orthogonal. Q1 or 0, Q2 or 0, or 1. So after this, rotation matrix like this, we do that. Well, this is our, Rx, our RZ, Rx, our RZ. After this, this is originally, gradient of velocity. After that, we get a new one. New one is the Z part, this part, 0, 0, lambda r. This is parallel to the new text. This is parallel. Or we say the new text becomes one of the coordinates, Z. If we think this is X, this is Y, then this is Z. You see X, X, X. This is X, this is Y, this is Z. So this is we need the first step is rotate the original vertex to be parallel to new text. This is a new text, 0, 0, lambda. It's a new text. It's a new text. To be that one. This is a new new coordinates. New coordinates. So originally it could be anything. So it could be X, Y, and Z. But now we need to rotate it. The rotated, that means we need to rotate. Rotate what? We could be this, be that, could be that. So this is, for example, we said is X, not X, capital Y, and capital Z. Capital Z, this is nothing else, it's the new text. So we rotated our coordinates. As this Z rotated with this one. This is rotated to that direction. There's a coordinates rotation. But of course, we still didn't determine Q. Oh, God. Well, right? Right, yeah. So we have rotated small x, y to the new coordinates, capital X, capital Y, and capital Z. Capital Z is nothing else, it's a new text. Well, as I say, we need to satisfy Q1 orthogonal to Q2, Q1, Q3, Q2, Q3. According to this, I don't want to give the very details. We can find Q1 and Q2. Even this is not necessary. We did find what is Q1, Q2, because they have 3 coordinates. Not only Z, you need to find capital X and capital Y. We can find it, yeah. we can find it. Yeah. By this calculation, I don't want to give the details. But we just based on this condition. 3 conditions, you see. Q2 also to Q1, Q3 also Q2, Q3, they also to each other. According to this, we can find the other Q1 and Q2. Q3 we already find it. Q3 is a new text, we'll find. But this is different from the nominal CI system. Nominal CI also 3 vectors, but not orthogonal. This is an orthogonal system. That's different. is also orthogonal system. But we found this already. Yeah, I just want to give details to the time consuming. So how to rotate it, how to get that. Okay, then this is I prefer to skip or jump. Yeah. So anyway, I just say we can use rotation metrics to rotate original small x, small y, small z to capital X, capital Y, capital Z. Capital Z is nothing else. It's mutex. That's I want to jump that. Yeah, this is take time. Yeah, I believe. Okay. So if this is capital, this is the gradient of v, the gradient of velocity. Well, this is capital, transpose. Then we do this decomposition, 3 parts. This is rotation, this is stretching, this is shear. Be careful that, I'll talk more. This shear is not Navier-Stokes shear. Navier-Stokes shear is symmetric. Symmetric. This is non-symmetric. This shear is non-symmetric. I will explain a little bit more why we use this non-symmetric shear. It's different from Navier-Stokes equations. So this rotation we don't have in the Navier-Stokes equation. And this stretching is real stretching. This is, in the solid mechanics, you always can transfer shear to the diagonal element. Diagonal always say stretching to be shear. You always can do that, yeah. But not for this. This is vortex. Vortex have the direction. They say they have stretching, it is stretching. You cannot rotate it or use other way, transfer this, the stretching to be shear. You cannot. This part is not transferable. In general, it is. The diagonal element can be rotated, become the shear, but not for this. Be careful this. When we talk about the turbulent flow. So turbulent is different from laminar flow. A lot of theories will be disappeared. Yeah. Be careful with that. Well, that's the conclusion. I need quickly. I have another to talk. Yeah, right. And so the conclusions here, G1 vorticity cannot. This is removed from our candidates. Yeah. G2 cannot. Q also have more problem. They not consistent with delta. Mutex is unique mathematical definition for local fluid rotation. I give a definition. Some professors axiom, not only the definition. Well, the axiom we don't know people agree or not. I don't know. Yeah, but I just listed as the. Just say, Mutex is mathematical for local fluid rotation. Unique. Well, people may not agree. Unique? You only one? Forever? Well, if you can find the two, give to me. I defined it. Rotation axis cannot be stretching. Stretching cannot rotate it. We define this. If we have second definition, give to me. Give to me, yeah. This is unique. So, then we have quantified research for turbulence. Well, turbulence is everywhere is a vortex. It's a vortex is not definition. Nothing can measure the vortex. Vortex is not definition. Vortex cannot be measured. Then conclusions, all turbulence is not quantified. Theoretically. Because you don't know the vortex structure. You don't know the vortex strength. You don't know that. The vortex strength is a turbulent strength. Well, the said vortex is the building elements and the muscles. That's not by me, by a German scientist. Well, this is pretty much a talk. We can talk later. Well, like SGS model, subgrid model. I would like to say it's not consistent with physics. They use called eddy viscosity. Well, I think Dr. Yu will talk more. Why? Why the subgrid model? Well, it is eddy viscosity. Why? Because you are real stress, or you talk about real stress, or you talk about the, subscale, subgrid scale. It is convection term, non-linear term. How to become eddy viscosity? How to become eddy viscosity? Viscosity is physically is the property of fluids. Like we have oil, we have water, we have air. They have different viscosity. How the viscosity changed by the turbulence? How to do that? How turbulence can change the viscosity? It doesn't make a long sense. Also, we just return back one step. You say eddy viscosity. Eddy viscosity is eddy. How become number? Eddy is the direction. Eddy is a vector. How vector become a number? So what's the conclusion? What is the conclusion? All the SGS model has no scientific foundation. Well, that's the conclusion. Well, if we don't agree, explain why. You talk eddy viscosity, right? Eddy is a vector. How a vector become a constant? So, meanwhile, then real stress. Real stress is the non-linear term. Eddy viscosity is a linear term. How non-linear become linear? How to do that? Well, I only talk about scientific opinion. When you talk engineering, we use that. It is likely approximated. Well, that's not science. There's no reason. You talk to me, there's no reason. So the conclusion is what? All of the SGS model has no scientific foundation. The conclusion is that no matter how good is your SGS model is not scientific foundation. So the conclusion is that. Well, if we don't agree, no matter, you say, I'm accurate, I'm pretty much good. Result, well, that's case related anyway. The case related. How do you know it's 0.03, not 0.025? There's no reason. Well, that's what I say, the impact. Because I think all of this fluid related. No matter there's hydrodynamics, aerodynamics, high speed, atmosphere, ocean physics, everywhere, they use the traditional, classical SGS model, vortex definition, which are no foundation, or scientific foundation. No matter how many years they do, no matter, no scientific foundation. That's the conclusion. So, we are few people, how much work we need to do. Every US society, they need to study this, not only fluid dynamics, AIA, ASME, every American society needed to study what's wrong with you. You give a lot of things. These things are lost scientific foundation. That's my understanding. That's my understanding, not scientific foundation. That's the impact. So as I said, it doesn't mean people accept my theory. But as I said, some people ask me, so we didn't find many local students, unfortunately, except for my students. Right? Even local, I cannot convince the local people in the UTA. In the UTA, they have aerospace engineering, they have mechanical engineering, they have all these departments. But I didn't see anybody from them today. I don't know what's the reason. One reason is people are busy to go home. Right? This is one reason. The other reason, that means their department is not well supported, I think. So how hard of our job is, how hard. Even I cannot convince our university. They're just very close, some of my friends. So that's what we talk about UTA. How about the American society? How about the American Academy of Science? How to convince them? We have a long way, hard job to do. From my point, well, you need to change everything. Believe me. Well, let me finish this. Yeah, finish this. Okay, let me go to the third talk. Sorry about that. That's what I say. We are discussions. Well, I don't mind to challenge. Fortunately, I think. Fortunately, I just say, U.S. scientific, NSF support me. Yeah, what's the question?
I have 2 points.
Yeah.
One is the representation of vertebrate and tensor using a large R or psi and ether. Yeah, I have also formulated in the similar way. And my comment is it can be expressed by more simple ways.
More simple, okay.
More simple ways. Using physical quantity that represent vertical flow symmetry.
Okay, symmetry.
Yeah.
The vortex you talk.
Yes, it is just physical quantity.
Symmetric, you say. Similar.
No symmetry.
Similarity.
Vertical flow symmetry quantity specify the skewness of elliptic vertical flow.
For separation flow separation.
No separate, just
for the regular turbulent flow. Yeah, okay.
flow.
Yeah, turbulent flow. Okay.
And then in that case, psi and ether is just equal to vorticity vector component parallel to the slope plane.
You use a vorticity.
Yes.
You use a vorticity.
Vorticity vector component.
Yeah, I say maybe minus something or plus something. You say, yeah. It's not a pure vorticity. Yeah. If it's a pure vorticity, well, this is okay when share is very small. Share is very small, the vorticity is okay. Yeah.
So when local vertical flow elliptic,
Elliptic.
we can specify short and long axis of elliptic.
All axis.
And
Okay.
then the vorticity vector component that I explained, just the component parallel to this short and long axis.
Okay.
Yes,
But then you talk about the real vortex, the natural vortex or something. There's group, there's not a point. Yeah. Here we mainly talk about the, point. Now, we talk about group later. Yeah. But we were listening. Yeah. Anyway. Yeah. Yes.
Just to understand the comment better. So basically it's like combining rotation and stretch.
You can, but you cannot do everything. They may not need it. Yeah. Well, no, that's my third lecture. We talk methods. Well, we talk a lot about theory or something like that. Now we need a realistic how to visualize vortex structure. So we just say, well, as we said, we have 6 principles. We already talked about that. We have Google, is always say that. So Nutex have the central axis and have angular speed. Nutex is twice the angular speed. Well, this meet the requirement. And we say we have the formula. The formula is clearly, is vorticity, is shear. Vorticity minus shear, you get a pure rotation. Yeah. Well, that's what I say. And Nutex is a mathematical definition of what at one point. We need to understand. At one point, yeah. Well, actually, we give the Nutex is 2018. Well, I believe this is the definition, mathematical definition first time. Since Helmholtz gave this definition 1815, it's about 160 years. And since then, we published quite a number of books, I think. This 1, 2, 3, 4, 5. We may have 6, 7, something like that. A lot, but maybe not many readers, they don't want to read that. But that's it. We really published quite a number of workshops, short course, and book. Now it could be 7, I think. So we already done. We published a lot of papers. Now we have a team. Some of people are here, some people are graduate or leaving or visitors, something like that. The current we have, not 3. I think something like 5, 6 students now. So Krishna and Mayan and Ria, I still have 5, 6 students now. So they are almost graduate. And the previous, we have a lot of students graduate from this group. This is not one-day work. Yeah, we need a lot of people, a lot of students, generation by generation, something like that. Develop code or write a paper. So many years, I think. So my group actually is supported by the U.S. Air Force, by NASA, by Navy. Well, now it's by NSF for almost at least 30 years, I think, over 30 years. So let's give a chance. The theory cannot be generated by like 1 year or 2 years. It cannot happen. Yeah, many years. Yeah. That we talk about contamination, G1 and G2. But the vorticity, if we write a formula, you see the vorticity. Or we know that. We know if we agree. Or it is rotation, Nutex. Then you have epsilon, Xi, and eta. They all share. So what they mean? This means vorticity is strongly contaminated by shear. Strong, very strong. You see? So how to use vorticity for vortex? There's no way if you have shear. You see that? There's no way to do that. About delta, well, it's complicated formula. Given by the Pushiba and Dr. Yifei, I think, given that. It's very complicated. That's the shear, and that's the stretching. Well, delta is quite. Q is same thing. You see, you have the stretching, shear, too many. It's contaminated. We talk vortex is rotation. Why you give these terms? So many terms. So when people use the Q, they didn't realize that. They didn't realize that we put a lot of shear, a lot of stretching inside your formula. They didn't realize that. This is mathematical relation formula. Well, even nominal CI is less, contaminated, but it still have share here. This share is, I think, this is anti-symmetric share, even for nominal CI. If we agree, we say Nutex is the only way, because Nutex idea is to get this rigid rotation, take away all of other share, stretching to others. That's the idea. Look at this formula. You see how serious of this vortex method, this vortex identification method. You could see that, how serious that. Yeah. Yeah, that's the eigenvector. I think some repeated, repeated that. We have original V, then we have V plus dV. That's the dV. dV, we say dV if it's all, right? If this is all, the dV only can be, stretching. dV can be, that means the same direction. It could be 3, could be 5. They're increasing. They cannot have this dV. This dV is impossible. Otherwise, it's not the rotation axis. So dV only can be stretching, cannot be that directions. So that's the basic idea, the main idea. Well, then you tell how to get this Nutex magnitude. Well, how to get this? So that's what I think, that's our new metrics we talk about. It's in the new system, right? Yeah. Then we can find this eigenvalue, and right, and then we can find the partial u, partial y, partial v, partial x. So we can find it. This is called omega z. This in this system we call principal system. The omega z equal to partial v minus partial u, partial y. So we can get this. So therefore, we want to find two unknowns, right? We need two equations. So we need two equations, right? So what is the two equations? First is partial u, partial x, partial v, partial y should be equal to a. Then this partial u, partial y should be lambda CI squared. Then this should be omega z. Then we get two equations, the red one. We get two equations, then we find the two unknowns. Omega z, we already know that. That's the vorticity. Yeah, we know. In the z direction. Partial, yeah, then we can find partial u, partial v, partial x. The two unknowns. So then we get what is partial u, partial y, and partial v, partial x. So we get this. Then we from partial u, partial y, and partial v, partial x. So then we use these two equations. We get the solution for all. For the all. Yeah. That's a new text. According to the two equations, I think how to get it. I think we use this equation, we take the square or something like that. Yeah. Or this equation, we get that. And that equation, so we have two equations, find the partial u and the partial y. So then we find the partial u, partial y, partial v, partial x. Then we get, finally we get all. That's all here. According to the two equations, I think. So we need to find the two unknowns, right? And we need two equations. Two unknowns is partial u, partial y, and partial v, partial x. Two unknowns. So solve this, we get partial u, partial v, partial y. Then we get the all. Yeah. When you get all. So that's, we said two equations, find the two unknowns. Right? And that's what said, we from this equation, this here, right? This equation, where's the equation? Partial vx, partial v, partial x, partial v, partial x, we just substitute there. Then we get this one, equal lambda I squared. Then we can solve the partial u, partial y. That's what we get at. Partial u, partial y. That's the new text. Partial u, partial y. Yeah, the reason you say why you use partial u, partial y, you don't use partial v, partial x. Well, because we pick the smallest. Partial u, partial y, partial v, partial x. Which one is the smallest? We use that one. But here we assume partial u, partial y is smallest. So we get that solution. We don't need to get two. Because they have share. So partial u, partial y, I think if we talk about the vorticity, there should be partial v, partial x minus partial u, partial y. But this is the vorticity. Yeah, that's the vorticity. See, right? Right. This is the vorticity, but that's not good. We only want to get the all. This will be all. Well, the all itself, well, we could call it 1.5. Well, this only, you can say, we put the smallest, because the smallest is antisymmetric. So that's why we assume partial u, partial y is smaller than partial v, partial. We only need to solve the partial u, partial y. That's how to get solved partial u, partial. Yeah. That's original what we did. Original what we did. Original, yeah. So you say we have partial u, partial y, partial v, partial u, partial. Well, that's what we want. We only need partial u, partial y. Because partial v, partial x, then we think is 1/2 ai minus plus epsilon share. So we only need to know the partial u, partial v. So that's what we get. That's how to get all. Well, there's 1/2 actually. Yeah, the all is the definition here. That's how to get the definition magnitude for the new text. Well, right? Yeah, partial v, partial x. Well, it is. They have the. We only need partial u, partial y. Yeah. Partial v have two parts: share and rotation. So we only need a part of them. So that's what we get. You see? So we only need is partial u, partial y, this term. But not this term. This term have some kind of share. Share, put here. So that's the reason how we get the formula. How to get the formula. Well, you maybe have questions. Why you pick the smallest part? Because smallest part is reach the rotation. Reach the rotation. So smallest part, yeah, is reach the rotation. Yeah. Well, and this is very important. You have two parts, partial v, partial x, and partial u, partial y. You pick the small part is partial u, partial y. The question why you put the largest? Well, you put the largest, that means you overspend it. When you put the small part, it's okay. This rotation plus another part, just like a bank. You have 2,000 you know, but you spend 1,500, okay. If 250, 2,500, overspend it. So that we don't want to overspend it. We want to use the smallest part. But this is also important for turbulence sustenance. Why? Why? Because, you know, this could make, you know, long, you know, symmetric. Why? Because you have partial U, partial Y. Well, you look at that. You have partial U, partial Y. You only use a partial U, partial. When you add partial V x plus anything, it doesn't change the mutex, or it doesn't change what is strength. You know? It doesn't change because you only use a partial U, partial Y, smallest. When you add more, for example, this is -1, for example, we say it's -1. This is 3. -1, 3, you only use 1, 2 share. Then you put more share, 100 share. So you get 5, you get 105 share. The vortex strength is not changed. You see? The vortex is not changed. Even your share is much changed. Vortex is much larger. It doesn't change the vortex strength. This is important. That's what we talk about the turbulence, you know, theory. They're not symmetric. But if we say -1, you change a little. You say, now we have -0.5, where your vortex becomes 0.1.5. If we change anything here. If we reduce them, it's just 0.5. So you get 1. It's not symmetric, but it's a share. They give all share. They give all share, but different rows. One change the mutex, one never. So this, from my point, this is one of a turbulence theory. It's not symmetric, not equal. Why? Why? This is the definition of a mutex. More important, this is nature. Nobody can change the nature. Don't think you give more vorticity, so vortex becomes strong. You give more vorticity, they never change. They don't respond. But if you change partial U, partial, it's still share. You give a little, change much. Well, this is just like a thermodynamics, second law. Right? The second law. So, if our room is closed, right? No heat, right? Yeah. Well, you can use the air conditioning, make it cooler, right? So you take the air conditioner back, they cannot recover the original, become hot. They cannot, right? For example, if we have some wall, 2 rooms, one's hot, one's cold, then you take the wall away, one room become cooler, one become hotter. When you build the wall again, they cannot come back. This we call the second law of thermodynamics. Right? Yeah. Same thing as the mutex. Same thing, mutex. Don't think you give the vorticity, you make a vortex stronger. They may be never. But if we change a little bit on the partial U, partial Y, the mutex will be changed. This is not reversible, not reversible. That's one of the reasons why turbulence is not symmetric. Because it's not symmetric. Your perturbation, it is random. Your perturbation is random. They may change the mutex, may not. But this is not reversible. The reason is why you ask me, why you pick the small one? Why you don't pick the bigger one? That's the reason. You only can pick the small one. If the small one never changed, your mutex never changed. Your big one, well, how change? You change. It doesn't play any role. Unless you reduce partial V partial X becomes small one. Partial V partial small one, you pick the partial V partial X. That's the nature. We cannot change the nature. That's just like the second thermodynamics. No, we cannot change that. Well, that's repeated, but we talk about that. Well, now we talk about methods. The Nutex tube, I think, I just talked about. I think this originally, I believe, my student Oscar, they tried a Nutex tube. That's a Vortex tube, pretty much. How to do that? They just take the circle, then put all these lines. This circle and put lines, they call it Nutex tube. It is a Vortex tube. Originally in the book, they also put a circle. They put a vorticity line. They call this is a vortex, and that's not a vortex. But this it is. This is a Nutex tube, this is a vortex tube. A vorticity tube, not a vortex tube. This is the tube. This kind of could show. This could show the vortex structure. Isosurface cannot. Isosurface just say, in this surface, every Q is equal. In this surface, lambda 2 is equal. It doesn't mean they're vortex tube. The vorticity, of course, is not. And what he do? He just pick, try to find the vortex tube, or core line, or something like that. He just take sections, find a large Nutex, then get a small circle, then put the lines. This is a Nutex tube, exactly Nutex tube, but a Nutex tube is a vortex tube, not an isosurface. This is not an isosurface. Not Q. What means Q isosurface? What that mean? That means that at every point, this Q equal to each other. How do you know this vortex structure? How do you know that? No reason. No reason. But this it is. This it is. Because this all the vortex, the Nutex line. The Nutex line, it is the, well, they maybe have different strengths. The Nutex, because you have Nutex field, right? It's a vector. You have Nutex vector is a field. So you have the field, then you can have the Nutex line. Nutex line form the vortex tube. This is different from isosurface, the total different concept. Yeah. Well, this is also use the Nutex line. The Nutex line will be, parallel, consistent with the with the vortex structure. Nutex line. Well, this also show that that's the vortex line. Well, that's the Nutex line, really. Well, this is a vorticity line. Well, Nutex line, vorticity line, so apparently Nutex line is parallel to the surface. How say vorticity line parallel to the? I just don't understand this. Yeah, I don't understand how to write a textbook by the imagery, not by the computation, by imagery. Yeah, you can find it. And this is the vorticity line. This is the mutex line. Well, which one is the vortex? Which one is the vortex? Well, they claim vorticity line is parallel. This is parallel? The parallel to the vortex? Make nonsense. That's also vorticity line. Well, I don't know how this textbook made. I don't know that. How they get this graphic? It's not graphic. It's hand drawing, right? Hand drawing is not really from the computation or from the experiment. No, just by handwriting. Well, this is from the computation. How we say this is the vorticity line. How say vorticity line is parallel? It's make nonsense. But this it is. The mutex it is. You see, and that's the vector parallel to the surface. This is not. This is orthogonal. Well, I really, you are mostly here as young people, I think. You are maybe easy to change the idea, but not for the professors. But I don't know where they get this graphic. They put it in the book. Where they get it? They by handwriting, by imagery. When you buy the computation, you will find that it's totally different. Well, even for the ring, it's also same. He said, ring also same. You see, that is independently. He said the news is parallel to the vortex ring. Well, there's a trick. This is a trick. What is the trick? In the ring is very strong vortex. Shear is very small. In that case, vorticity almost equal to mutex. If you try that. For the vortex ring, vorticity very close to the vortex. Not for legs, nominal vortex. Not. You can check that. That's the reason they claim they find the good methods, excellent methods to identify the vortex. I'm not sure Dr. Xu knows that, right? They published a paper, JFM or something like that, right? They say we got the good methods. For what? For vortex ring. For vortex ring, congratulations, you are correct. Because the share is small, but not for vortex. Not for vortex. Vortex, they're orthogonal, they're not parallel. And that's just joking, I say. Well, that's a paper published in JFM. Many such papers. So they find a good method for the, well, as I said, for this case, Newton is correct. What is it likely to be the similar? Not for the legs. No. The reason is why? Because shear, this is very small here. Here, I believe, according to omega method, there's a 95% mutex, 5% shear, about. Well, this is what I already show you already. That's what we get at. The sound to me is very clear vortex structure. Then we talk other method, now omega method, I talked already. The omega method is an easy method. It's very easy. Don't use that. Well, this is almost very similar to Q, but better than Q. Why better than Q? You don't need to adjust it. You don't need to adjust it, much about the threshold. Also, they can capture both weak and strong vortex. They capture more vortex structure. More vortex structure. The omega method. That's the omega method. It's 2016. I think right now they have 746 or something like citations, the omega method. Well, omega method is the first step we can try. And this will be much better than Q method. You don't need to change much. Well, some people say, it's still difficult for me because the tech product has the Q method there, right? You don't need to write anything, you just use the tool. They could say it that way, right? Well, omega at least you need to find A, find B, and find epsilon. Well, but you will find it more convenient. You don't need selected, you don't need a selected threshold. You put 0.52 or 0.354, it's okay, you decide. Then you get almost unchanged vortex structure. This is one method, this is the only method. We given, I think 2016 given, the omega method. Omega method is still, I believe, better than Q, lambda 2, lambda CI, and delta, better than all of them, which with very simple, very minor change, very minor change. The omega, that's why we use the omega method. That's what I say, why we use the omega method. There's one method, omega method. That's I recommend it if we are very beginning, very starting point. Well, we just, while we are kids, we just make very little change, we get a better result. You will find a lot of new physics. Why am I saying that? Because I talked to some people working for the, turbo machinery, where they have sort of vortex nicking. Or they say they have two major vortex around turbine machinery. One is the central vortex, very strong. The other is aside, quite weak. They use Q method for 1 year. It's very difficult to adjust it. They still cannot capture the weak vortex. They capture the strong vortex, then cannot capture the weak vortex. Then I have to adjust the, threshold. Then adjust the threshold, then mass threshold very small, and then it's not a vortex. It is just an area. They struggled this for more than 1 year. Then they know I give the omega method. One time they're successful. Both vortex captured. That's why they invite me to visit the guild. That's the other story. Yeah, that's for the turbine machinery people. They use omega method. They find a lot of new physics. When you use Q, you totally ignore that. Because one vortex is very strong. When you use threshold, then you use large threshold, the weak vortex totally disappeared. Then you reduce the threshold, then you cannot get a vortex. You get one vortex, everywhere is vortex. This has happened in many cases. In many cases, like I think, especially in turbine machinery, it is, they call it nick, vortex nick. Vortex nick. That's I recommended this. It is a beginning. The omega method, we can see that this is much better than Q method. Yeah, I believe. Yeah, and new text omega method. Well, omega method, you can say Q omega method. They're based on Q. The advantage it is, can capture both weak and strong, vortex. But they're still in the Q range. The idea is still, but relative Q, you could say, the relative Q, you could say that. Then we talk about new text. Sorry. Huh? What is it? New text, we call the new text omega method. And the basic idea is we still want to get the relative mutex, not the absolute value. But absolute value of mutex is good because it's accurate. Relative is not that accurate. But how to get that? How to get that? So we know this is omega method, B over A plus B, A squared, B squared. So what I did, yeah, we get alpha, we get a beta, we get a Xa, we get a eta. And beta looks like is the vorticity. Alpha look like a shape, like. Lambda like the stretching. So what we did, we just take this Xi, eta, we know this is shape, take them out. Take this out, yeah. We still keep the beta, alpha, lambda Ci, lambda R. But this method, finally we get this. Finally we get this. So this we call the mutex omega method. The beta square, beta pretty much like a rotational part. Alpha pretty much, yeah, like the, the share we already take out. I think we take out the Xa eta, we didn't take out the epsilon. Pretty much like that. And so explicit formula, we use this here. But we come back to vorticity, R is a mutex, lambda Ci is eigenvalue, imaginary part, lambda Ci real part, lambda R real part. So pretty much like this. That's the we call the mutex omega method, or we call it modified. I believe this method was a good advantage, but this method is mutex based, not Q based, the mutex based. Second is relative. I think according to my impression and our own experiences, this method will give very good vortex structure without threshold change. Little, very little, not much. Just like say 0.5 or 0.52, it's always like that. But it's mutex based, this method. As I heard a number of resources, they all research use this formula for the vortex identification method. Because this method, they don't need change, they don't need adjust. Don't need adjustment. This is also very clearly omega is vorticity. R is mutex, we know the eigenvector. And lambda Ci, you know that is eigenvalue. Imaginary part, real part, real part. Epsilon you need given. I believe some Chinese university, I think, they use this method as a standard method. It's still isosurface. Still isosurface, but without change, much change to the threshold. It's insensitive to threshold. Okay? That's what we call mutex omega method. All of this still isosurface. That's the modified, I think, modified, and the advantage is where it's insensitive and no share contamination. All share will take out, but you still have something like stretching contamination. Yeah, the combined idea mutex and omega method. This is published. You look at these pictures. This is made by this method. I think it is a very clear vortex structure for the fluid transition. You see that? There's one of the students made that. She graduated already. Give me these pictures. Yeah, it is very clear. Show the vortex structures by this method. They pick the omega L 0.52. Well, epsilon, be careful that you need to adjust it. But not much, not very much. Well, they say, well, if we use Q method, well, you see that, well, that's pretty much, you still can see that, similar structure. Not exactly similar. And then we tried, well, apparently we still keep this vortex structure. But look at Q, it disappeared. The ring disappeared, you see. The two same cases, at the same, time steps. They're same time steps. Same data, does I say. Same data. When you use the Q method, they use this Nutex omega method, where you get different vortex structures. You see that? Yeah. This clearly, they keep the vortex structure. You see that? Well, you see this Q method. When you say, you may be too big, Q too big, threshold too big, well, you can reduce to small. Then what happens? You cannot see any vortex structure. They just link together. So, you understand that? This is, we just make sure they have similar structure at the early stage, and then you find this. So, as I said, we recommend this method if you still want to use isosurface. This is still isosurface, but it is Nutex plus omega method. More. Well, more. You see, now we get high, 75.7. The basic structure is still there, even you change the threshold. But look at this. When you change it, totally lose these structures. Totally lost. You see that? Yeah. Well, I'm more serious about the Nutex core line. Well, this Nutex core line, I think I give the definition is that. So, for the isosurface, we know that dr is 0 because in the isosurface, they are same, all the same. The strength, Nutex strength is 0. Q strength is 0. So it is isosurface. But the isosurface, in general, orthogonal and DL is orthogonal. When we talk about the gradient R is the so we talk about the isosurface. Isosurface, we know the R is constant. If this then we talk about we talk. Suppose this is R, but on the Nutex, they're same as the Nutex. Same as the Nutex. But how about the gradient of R? Gradient of R is that direction. They're orthogonal in general. But when you get a vortex center, what happens? When you get a vortex center, what happens? If this is a core, we call it core line. Core line, so there R, and this is R, they are same. One, if it's normalized. Or we say, that's the definition for core line. The gradient R and R, they're parallel. Then we say, this is a core line. Well, some people talk about like hurricane. You have a large vortex, then you have many 100,000, small vortex. Use this judge. This gives the core line. You meet this condition, you have vortex. So you can find many. Yeah. You use this judgment. Make sense? Make sense? Yeah. So usually grade R, it is orthogonal with R, but in the core line, they are same. They cannot same. Yeah, they are same. Grade R and R are the same. That's the definition that we put here. That's the original work. Well, original work, well, one of the students used that way, and they picked a large mutex and then draw the mutex line. They say it's a core line. Well, Dr. Xu said, you did publish one paper, right, about this. Also, we try to develop some software, right? Well, unfortunately, it's not easy. Yeah. So far, Dr. Yu will give the talk about his method, how to draw the core line method. Well, how important is the core line method? The no threshold. No. No threshold. We don't need any threshold. Unique. That is unique. You can never change it. If you give the data, one data, one picture. Unique is different. Like one data, hundreds of pictures. Depends on threshold. This we call the core line method. That's I very, emphasize this method. The reasons why. Well, who gave the turbulence vortex structure? Who gave? Can you show me one example? Because you use different threshold, different method, you get different picture. Which one is the vortex structure? How do you know this exact vortex structure? Nobody knows. Nobody can answer. But mutex core line can answer. They're unique. They don't have a second one. They're unique. All others, in other words, we never have any vortex structure for turbulence. No. If you look at the book, as I said, one like an insect, the other one like a fish, the other one like points. Which one is vortex structure? Which one? No one. So this core line is important. I believe it's important. Unique and threshold free. Well, and this is, we just say, well, we look at this vortex. You see that? Yeah, they same. Gradient R and R the same directions. Yeah, we will see that. That's the isosurface, that's the core lines. We get it. That's local, we call local maxima of mutex. Really, this problem, same problem as how to find local maxima of mutex. How to find it? Same thing, same question. Mathematically, it is find local maxima. Well, you need the first derivative is 0, second derivative is maybe negative definite. As I said, all identification methods depend on threshold. A different threshold give different vortex structure. There's no problem. Some say we need a proper threshold. There's no problem. Not proper. What means proper or improper? We don't know. The mutex core line is unique. The mutex core line gives the unique vortex structure, the only one, I think. I believe, do we have core line? We do. This is given by Dr. Yu, I think. This is the gradient of the mutex. You see, they do have core. They do have, local maximum. They do have. This is not just by imagery or by guess. It is truth. It is a truth. They do have core line. Well, you see that? We can find it. We can find these core lines. Then we can find these core lines. It's not the line. What's the advantage? Well, it's line. first. Second, they have the strength. The isosurface is not strength. Isosurface means on the surface, every Q are same, lambda 2 are same, Nutex is same. That's isosurface. But this is not. You can find the red one means strong. Blue one means weak, not the green one. Blue one means 0. So you can see, this core line, they have different strengths. Yeah, this is more. They use this isosurface. This is core line. That's the core line. The red one means very strong. Well, this is made by some students. So you see that, yeah. This is, you can see that. This is the core line. This could be the real vortex structure. The real vortex structure. So the core line is the only one. Also, they can shoot strength of the vortex, shoot direction of the vortex. And well, detail, I think the Dr. Yu will talk about. I need a quick. The core line, I think you can say, well, I don't want to say much to it. Yeah, you already repeated that. So then we can see this the core line, and we can see this core line, and I believe this is made by Dr. Yu, right? Yeah, I think he gave the core line. I think more recently, by the automatic method, and this is also by core line. Well, you can count this Q method. The Q method get a different vortex structure. It's total different. Just pick different Q, 0, 0, 1, 5, 0, 0, 5. Well, the core line can never change it. And then we give more core lines example. This did by Dr. Yu, I think. Yeah, he did. And he did also, core line. And well, that's a red one means strong. That means very strong. Maybe in the leg, the vortex of the legs, well, the leg generally rings. Leg is very strong. Leg, not the leg. Leg, not leg. Very strong. Nutex core boundary transition, yeah. That's what they do. Find the Nutex, core line. This is isosurface, this is core line. As a surface. Well, more recently, I think the Florida, the same give the data. We asked them to use the Nutex and I'm not supposed to talk this now. Well, that's give this is they called I'm not sure contour or something like that. Vorticity. That's called vorticity. Okay. Well, that's very not strange. We see in the newspaper, we see this website, we see in the paper, but we never see this. This is what? This is Nutex. Well, this really we don't know where is the hurricane center. We don't know where is the hurricane center. That could be here, could be there. Well, this is Earth. There could be 100 kilometers difference. How for us to do the right forecasting? How to do that? How to do the right forecasting? This could be 100 kilometers difference. Well, look at the Nutex. Look at the Nutex. 1 point. It's not 100 kilometers. That's why I asked him. Well, he may not agree with me. Well, why just report the Nutex? Why you report the vorticity? This is vorticity. Why forecasting vorticity? Why do that? This is in the newspaper. It's in the website. Why just report this? People know that. That's not in last year. It's not in Tallahassee. That's in Tampa. They report in Tallahassee. They say we destroy the whole Florida State University, but they landed in the temple. Because nobody knows where it is. That could be 100 kilometers away, But you use Nutex, you see. They give you exact location. Well, I don't know. It's not one day. You can persuade them. Not one day. Well, the same thing. The same thing you can see that. Well, this is very hard to find what is the vortex center. Well, this is easy. Find about the Nutex. There's impact. I say, well, everywhere you can use that. And the comments made by different people, I think, including Dr. how to say, G.R. Tozzi, Castros. That's your name, right? Yeah. That's your name, right? Yeah. G.R. Tozzi, yeah. No, your name? I think you are the first author. G. Well, I thought you are the first author. First author. They give the comments, right? And also our others, they give the comments. From their point, well, Nutex is the best, more accurate. No, I didn't list all of them. Many people say, well, when you use a Nutex, so it's more accurate than all others. Well, because accurate is more important. As I said, the tornado is in Tampa, but you report, you focus it in, says Tallahassee, where it is. Where is Tallahassee? Is Tampa or it's not? Right. So we don't do that. That's the conclusion. Say. But this mainly I talk about the methods. So methods, you know that. What are the methods? Omega method, Nutex method, Nutex tube method, Nutex colline method, and Nutex omega method. All of the methods you can try. Where they get more accurate, more difficult. Well, the easy way, omega method. The easy way is Nutex isosurface. This is still isosurface. But don't think they're the same as Q. Pretty much for the strong vortex, they're similar, not everywhere. Okay? So I think I should stop it at the conclusions as reference. Thank you.